Bismillahirrahmanirrahim. This is the second video of the series. Here we'll be solving a shunt generator question. This is a part of exercise 8.17, question number 2.1 from the notes by Dr. Sattar from University of Anwar. And this is on the request of a student. So let me just recall that in the previous video we had drawn this open circuit characteristics curve, and this is basically between the IF, that is field current, and the generated voltage E, or output voltage when there is no load. So this, with the help of a MATLAB, you can easily plot, and the graph is for 850 RPM. Now, what is a shunt generator? Briefly, in the shunt DC generator, the field current in the machine depends directly on the machine's own output. So this is the armature, or this is where the voltage is produced. This is field current and load. So any voltage produced is actually feeding the field. So the field current depends on the machine's own output. Now, when there is no load, then this output voltage Vt, or it is Vf, will be same as the armature generated voltage, because without load there will be hardly any current flowing, and so the voltage drop here will be negligible, and therefore EA, or we can call it Vt. EA is generated voltage, Vt is the terminal voltage, and plus IF. So we can plot this graph, which is called the open circuit characteristics curve, or also called magnetizing curve. We'll need another one also, another graph, and this is called the resistance graph. It is between the field current and the field voltage. So this graph is, we call RF here. So we'll be using these two graphs. And in the book, professor has drawn this curve already for various resistances. So we'll be discussing each of them. This red is RF line when the FCR is 0. FCR is the field control resistor. And when FCR is 10, then we get the green graph, and when the FCR is 20, then we get the this magenta graph. We'll discuss each of them. From here you can see that the terminal voltage Vt is EA generated here minus IARA, so drop across the armature resistor. And as I mentioned, when there is no load, so no current is flowing, therefore this voltage drop will be 0, and therefore the terminal voltage will be equal to the generated voltage. Okay, the generator no load voltage is where the magnetizing curve intersects the field resistance. So we'll see this, how to calculate the no load voltage. But from here you can see this is the magnetizing curve, or the OCC curve, and this is the resistance line, field resistance line. So wherever they intersect, that is the point from where we calculate the open circuit or the no load voltage. Now let's come to the question. We have a shunt generator, and it is operating at a speed 850 RPM. The field resistance is 20 ohm, and then there is a variable, or the field control resistor along with this. And from here the formula of total resistance, total field resistance RF, is FCR plus RF dash. The question is, what is the no load voltage when the FCR is shorted out? That means 0. Next is when it is set to 10 ohm, Third is when it is set to 30 ohm. Then next question is find the critical resistance and short circuit current. Part C is what is the critical speed when the FCR is set to 10 ohm and 30 ohm. And part 4 is what is the minimum speed at which the generator can build up. Let's do the first one. What is the no load voltage when the FCR is shorted out? So short circuit. We already have the OCC table. Now all we need is IF-VF graph. This graph we need of all. And how to calculate this graph. When FCR is 0 from this formula, RF will be, this is 0 and RF dash is 20, so 20 ohm. And so the VF will be IF into RF or IF into 20. So this will call the general equation for this particular RF value. And by plugging in the values, VF is calculated from general equation for different values of IF. So putting IF is equal to 0, 1, 2, 3, 4. You can use the Excel sheet. So quickly you get the output. This is the output, and this is in tabular form, and we can then plot it. We'll see in the next slide. Now IF versus VF line is actually the RF line for that FCR. So this is where it is. This was the OCC graph, and this is the RF line for FCR0. And you can even see at 0 current, it is 0 voltage. And let's go to the end. So at, let's say 300, the current is 15. So you can see if we from 15 we draw a line just touching 300, and you can join this to get this line, RF line. Now wherever this intersects, that's what we said, we'll have the no load voltage. The generator no load voltage is where the magnetizing curve intersects with the field resistance line. And from here you can see that it is 257.5 volts. So this is just a guess, but since this is what has been given by the professor in his notes, so I'm following this. But if you are a little bit out in guessing, no problem, you have the almost correct answer. Okay, the next is when the FCR is set to 10 ohm, we follow same technique. Now FCR is 10, RF is 30, then our VF equation will be this. And here also we'll put the various values of IF to get the table. Now this is the table for FCR 10. And when we plot this in our graph, we'll get this graph, the green color graph. And the intersection line now, you can see with the OCC is this line, and which is giving V no load or EO 0208 volt. This was the second one. Now we come to the third one, 30. Same technique. We instead of there should be 30 here. The total will become 50. This will be general equation. This will be the table, and we plot it. It will be the magenta line. And from here you can see that it is intersecting almost at the bottom. Although from this graph it looks to be more than 25, but if you draw it correctly through the MATLAB, you will get this value. So it is 24 volt. The professor has taken, so I'm taking that. Okay, now the next question deals with the critical resistance and critical speed. So let me just find what is the critical resistance and critical speed. Okay, so there are two things we need to discuss before we proceed further. What is the critical speed? It is the minimum speed of the armature which is required to build up EMF by the generator. You know that the armature is rotated by some external force to generate voltage. So the minimum speed that will start generating voltage is called the critical speed. And then there is a term called critical resistance. It is the maximum, sorry, not minimum, maximum field resistance, total maximum field resistance above which the generator could not develop EMF. So if we have more than the maximum, then this generator will not develop EMF. These are the two conditions actually for controlling the speed, the uh, critical speed and critical resistance. Okay, now the question says find the critical resistance and short circuit current. First of all, the critical resistance is a slope to the OCC. So if this is the OCC line, so we draw a line which is tangent to the OCC line. That will be the uh, mm, critical resistance line. And any resistance greater than that, the generator voltage will never build up. So like if you have a resistance R3, there will be no output. So the resistance has to be less than the critical resistance. For a shunt DC generator to build up voltage, the total field circuit resistance must be equal to or less than the critical. So the resistance has to be equal to this or less than. Even equal to is very dangerous because the output will keep fluctuating. So it has to be slightly less than R2. Now the first part is find the critical resistance. The easiest way to find the critical resistance is that we draw a tangent line to the OCC and take any point of intersection between them. Like here, if this was the OCC, we just draw a tangent line and we take any point. So for example, we can take this IF1 and find the um, um, EAO, or we can take 2 and find EAO, you can take 3. So let's see. Now RCR then will be, if we are taking 2, then the voltage divided by current is the resistance, V divided by I, so 80 divided by 2 is 40 is the critical resistance. Then the next part of the same question is find the short circuit current. I short circuit. Now when we short circuit the terminal, the current flowing through this will be the short circuit current. And at that moment the terminal voltage will be 0 because there is no resistance. So I into 0 will be 0. So, and since all current will flow through this, so no current will flow through the field winding, therefore IF will be 0, VT will be 0, and IA will be ISC. So the current through the armature will be same current as the short circuit current. And then EA, that is voltage here, will be the residue voltage. Since no current is flowing through the field winding, so this will not generate any voltage. So whatever is left over in the generator, in the magnetic fields, that is called the residue voltage. And generally, because of this, the generator starts. But if it does not start, then we have to supply some external voltage here to restart it. Anyway, in this case, we need to find the short circuit current. So from here, using this formula, Vt is EA IARA, and since Vt is 0, then E residue minus ISC RA, and so ISC will be E residue over RA. Now, how much is E residue? There are two ways to look. If we look at this graph at the point here, when current is 0, it is 20. or even from the table we can see when the current is 0 IF, then we have 20 volts. So this is residue voltage, and RA is given in the book, it is 0.25. So I short circuit is 80 ampere. Then what is the critical speed when the FCR is set to 10 and 30? Now, let's say this is our resistance line. This was our OCC. So any curve below this will be a low speed curve. So this one N1 is greater than N2. Now to find the critical speed, what we need to do is that we should have a curve which is tangent to, or this line is tangent to that curve. So we know that if it is tangent to any curve, that is the critical speed or the critical resistance for that curve. So this will be the critical resistance, and the curve itself will represent the critical speed. So with this background, now it is the minimum speed of the armature which is required to build EMF by the generator. So all generator works above the critical speed. So the generator has to work above the critical speed. If it goes below, the generator will not start. Okay, so to find the value, we'll use this formula. This is our critical speed N1. Take any value of IF and draw a vertical line. So we'll use this curve now. And for FCR10, this is the line. And instead of drawing a curve here, we just use this line. This will be tangent to that line, and compare these two values. So we are comparing it here. We have to be towards the lower end, because at the lower end is the tangent more prominent. So let's say we are here, and at IF2 we have the intersection with the OCC we know is EO, which is 80 in this case, and the intersection with the resistance line is EA, which is 60. So we'll plug in that values here. In the book, he has used 30 and 40, but it's not very clear from here. So I'm using 80, and that is at IF2. So we have 60 and 80, and speed is 850. So from here, the new speed or the critical speed is 637.5 RPM instead of 850. On the second case, for FCR 30, so now this is the curve we'll use to calculate and compare with the OCC. So now this we are comparing with the OCC, so intersection this is EO, and intersection with the RF line is 100, that is E1. So putting these values again, in this case you can see the N1 is 1062.5 RPM. As we are going up, the speed is increasing. And finally, what is the minimum speed at which the generator can build up? So for minimum speed, we know that the RF line or the FCR has to be towards the lower end. So FCR 0, we have the minimum resistance, and the graph to which this is tangent will be the critical speed, or this is the minimum speed that we'll need. What is the minimum speed for which the generator can build up? So the minimum speed we'll achieve with the minimum RF line, and that is for FR0. We're using that. And now the same formula, speed formula, same technique, two intersecting points. So this is E1, and the one with the OCC will be E0. So E0 is 80 and E1 is 40. So using the speed formula that we used before, 40, 80, 850, N1. So N1 is 425 uh, RPM, not VPM, RPM. So I hope you have been able to follow this. Please let me know your comments. Thank you.